think that's better contrast. So I work at NASA headquarters in Washington, D.C. NASA has many scientific centers where the science is made. I work at headquarters where science is being administered. So it's the place of money. So I'm trying to give money to move science forward. I got interested in vegetation already at a very young age, 3. And a little bit about my life. I was born in Leningrad, which was former USSR, Soviet Union. And lived in various cities in Russia. Was Moscow, Leningrad. Also lived in Caucasus because my father worked there for a while. And in Siberia, where he was invited in a scientific center near Novosibirsk, where I graduated from high school and also studied there for a couple of years in Novosibirsk University. Now, in '78, after working in Moscow for a year and a half in the same room with Sasha, I immigrated to Israel, was here for at least 7 years. So I had fun. I got my PhD at Tel Aviv University. I served in the army. I learned in the army, IBM, PL1, SAS. Also, I met my wife at that time. We had first daughter, so our first daughter was born in Kfar Saba. And that's how I looked about 40 years ago. A little more plants on my head. Probably nobody would recognize me now. And since after doctorate, usually people go Chutz La'aretz, so I got a special reward. It was a National Research Council of the Academy of Science in Washington area, and was there on postdoc at NOAA, National Oceanic and Atmospheric Administration. We got second daughter there. And I got a federal job in 1990 at this National Oceanic Atmospheric Administration satellite division. That's where they have satellite division. The main thing at NOAA is to do a forecast. It's a meteorological center. And ocean studies and other atmosphere. And if you see, there's no L in NOAA. But I was in the land research. So they always make fun that there's no L at NOAA. But yes, there is a land branch, and I was working, and I published many articles. And I'll show you now what was my major. Now, 1990, I came here for an interview to get a job, and actually they told me 99% I will be working here. So I started thinking how I will be going from here to NASA Goddard Space Flight Center in summers like I'll do, and how I will rent here, place Megurim like right here next in Givat Ram. And then after Professor Mintz, who was really my major protege, he was pushing me to come here, and died. And after that, in July, they told me that they don't have place for me. But I already had a civil servant position at NOAA. I already was working there, so when I met here for interviews, I met with a professor at geography department who said that, oh, patriot or idiot, he has already permanent job in America, was come here, and I said I'm probably both. I wanted my girls to become Israelis, wanted to move, although I knew that in terms of career, probably it would be not as good as possibilities in the satellite center in America. But we stayed there, we bought a bigger house. And I worked 14 years at NOAA, including before I got citizenship, before I got a federal job. And we got stuck in the greater Washington, D.C. area, which is Maryland. And at a certain moment, 23 years ago, I said to I tried to get promotion at NOAA, and they didn't give me. And I said, look, I told my boss I can work, or I can work on getting another job. And he shrugged his shoulders. So I looked at the announcements. A week later, I got an interview at NASA, and the rest is history. I've been with NASA headquarters for 23 years, already not doing science like I was doing in NOAA as a researcher, but administering science, or you can say bureaucrat. So, that's the time when I was in Hydrometeorological Center in Moscow, working in a small room, probably quarter of this room, with several people sitting, and Alex Kain was sitting next to me, working on his stuff. And I was working on boundary layer parameterization in the general circulation model that was at that time adopted by the group there. I did my PhD in climate modeling, so I was a modeler at that time. And I did it at Tel Aviv University. Since I came here to look for possibilities of getting a PhD here, and also I looked in Weizmann, but I was already in Ramat Aviv, living in Beit Brodetsky, Mount Olim, and it was a 15 minutes walk to Tel Aviv University, and there was a professor who was interested in the students, so So I'm old enough that I worked with punch cards. That was in Moscow. I'm old enough that we had technical drawers for my PhD dissertation. Now, of course, you do everything by yourself with PowerPoint and so on. And transparencies, that's what we used until now. And this is my PhD dissertation. This is about geobotanical feedbacks with atmosphere and land surface. So at NOAA, my research was with AVHRR data, with advanced very high resolution radiometer, which is a few kilometer resolution, but daily. Cloud detection was just to screen clouds so we can see the surface. So my interest was to look at the surface to derive albedo, temperature, vegetation parameters. And I had some application, drought monitoring, mapping anomalies, and research with geostationary data. Geostationary satellites are looking at the same, hanging over the same area compared to polar orbiting satellite with the VHRR, which looks at the whole globe. So since 1999, until now, as Putin in his presidency, 23 years, and managing the program called Land Cover, Land Use Change. I'm also a program scientist for two satellites. One is Landsat, another Terra. I'll talk about Landsat a little more. So this is a one glass description of the program that I manage. This year we celebrated 25 years of the program. And during these 25 years, we had over 300 projects, over 800 researchers, and over 1,000 publications. This is a description of what's the vision of the program. And the main thing is to provide the capability for periodic global inventories of land use and land cover from space with satellites. The content of the program is mostly three parts. One is the detection and monitoring, another impacts and consequences of these changes that we monitor, and the rest also another third, like synthesis or adaptation to climate and so on. Because it's land cover, land use program, land use means that the people involved, very important, talk about human dimensions. So the socio-economic science part is an important component of the program. It includes impacts of changes in human behavior on land cover land use change, impacts of land cover land use change on society, so it's a reverse, and adaptation to climate change is another part. So a little bit about why we're doing all this. So four things of on the Earth system and its responses could be stratified into natural forcing and human-induced forcing. Natural forcings are because of the sun, solar variations, volcanic eruptions, are results from dust or wildfire smoke, and human-induced forcing because we add trace gases into the atmosphere, we add the changes at land surface characteristics because of different activities like agriculture or deforestation. And then responses to these forcings are in changes in atmospheric circulation, water vapor, clouds, precipitation, and amount. But what's important is that these changes, this changing land surface characteristic lead to surface heat and moisture fluxes changes, as well as changes in ecosystems. Now, the drivers of the disturbance and stress that lead to those changes. Okay, so these are the drivers of disturbance and stress. Natural could be natural hazards like fires, droughts, floods, hurricanes, tsunami, landslide, earthquakes. Invasive species like sometimes locusts come in, or tree beetles eat the forests and affects disturbance in forests. But the main thing is what they're talking about is climate change, climate variability. We're more in the program interested in anthropogenic drivers, like effects of political changes, technology changes, population dynamics, migration, and the exploitation of forests or landscape modifications like urbanization, agricultural changes, cattle raising, wetland exploitations like mangroves. So all of this gives you a description of what the program is interested in. And now we're talking about the consequences of impacts of those drivers. So this morning is probably not a good example with the sound. Sorry. Sectors could be all forest, agriculture, rangelands, wetlands, or urban, and studying all different processes, like in water cycle, water quantity and quality, changes in carbon storage and release, degradation of habitat and fragmentation, and atmospheric composition and pollution, air pollution. So land surface is part of the Earth's climate system. Why do we need these observations of land cover and land use change? So because the major driver on land use change is that population has been increasing unprecedented rate and has profound consequences in society. Just about a couple of weeks ago, it was announced that we hit 8 billion in terms of the number of people living on this. So I think that and it all leads to a greater demand in food, wood, water, biofuel, shelter. I think that we underpredicted because 8 billion looks a little later. We came to 8 billion a couple of years at least earlier than it was predicted by this graph. So I will talk a little bit on these various sectors like food, water, shelter, and climate, just to give you a general picture of what the program is working with. They talk about climate change. So land cover change is often referred to as second global change. The second global change is what you can observe on the land surface. This is a cartoon from long ago showing all kind of processes in the atmosphere, or hydrology, ocean, and everything. But also there is a part that shows human influences here. And you can see here the agriculture fields. This is a factory and transportation. So all these different things that affect the environment and probably climate too. So changes in fluxes affect land surface and lead to changes in human behavior and land use cover. Land cover changes lead to changes in ecosystem, and it could be natural and human induced, as I mentioned before. And the surface energy fluxes affecting the changes in ecosystem structure. Now, some changes occur on a regional to continental scale rather rapidly, and they could affect global climate. Skip that. All right, so this is just a second. I'm showing. Yep. Okay, so we know that the Earth is approximately covered by ocean, with except for 30% that is land surface, and 80% of this surface is directly disturbed by humans. Almost half, 40% of land surface is covered by cropland and pastures. That's why it's important to talk about food. During the last 40 years, our harvests have doubled because of the efficiency and improvements in agricultural activities. But also, there have been a lot of fields created by clearing of forests. So forests are affected by agricultural demand, or by food demand. 12% in increase in cropland over the last 40 years, and that mostly because of the clearing in tropical forest areas. 10% were lost during this 1990 to 2005. This is how state of Rondônia in Brazil looked in 1975. You see more or less intact forest, Amazon jungle. But that's how it looked in 92. Less than 20 years later, you see the famous, known structure, fishbone structure, where they build a road, and off the road, smaller roads. That's how they clear the forest gradually. And in 2001, you already see almost the whole area is denuded of jungles. What is it for? Mostly to, I'll show you now, but mostly for either cattle grazing or agriculture. So we've had already some products for the globe, like tree cover, extent, and forest loss and gain, globally, in different colors. If you know, the mixture of these two gives you magenta. So there are places where loss and gain kind of balance, and this was done at the University of Maryland. So we can see the rates of changes in forests in different places of the world with a 30-meter resolution. Well, what's interesting is to see how this loss of forests is by drivers. So by color here, you can see the differences, different drivers, like forestry or shifting agriculture, green and yellow, or wildfire. You can see it's mostly in boreal forests, or commodity-driven deforestation. So Brazil. And now you can see why it's important to talk about Brazil, because it's half of the global primary forest loss during this past 20 years was in Amazon. In fact, just a couple of years ago, it was the highest deforestation rate after 28. It was going down, and then it went up. So what was the primary reason for deforestation there? It looks like the main area for cattle grazing is in Brazil. So Amazon is being cut, and forest fires, specifically for cattle, for rangeland, to cattle to graze the grass there. And you see the maximum is right there. It's the results of the World Resource Institute. Now, concerning the cropland, we already have made maps, also at the University of Maryland, and you can see here also some changes going on. So this is also available. Now for agriculture, you understand that the water is the biggest important component. 70% increase in irrigation cropland in the last 40 years occurred, and agriculture accounts for 85% of global water consumption. It's a huge proportion. What's interesting is that the irrigated fields are only 16% of all fields, but they yield 40%. Oh, I forgot that I have this. 40% yields from 16% of irrigated fields. Next, I want to touch on a little bit on the shelter. In 1900, less than 14% of the population lived in the cities. And today, more than half of global population live in cities, and it's expected to increase. So, what's happening? I chose the place where Israelis can go now to visit. It's Dubai. In 73, that was a little fishing village. You don't even see where, maybe somewhere in the north a little bit. 73. 1990, that was already quite an urban center there. And that's Dubai in 2006, 15 years ago, 16 years ago. Can you imagine what's going on now there? And now, 15 years ago, they already had this 7-star hotel, all these islands built up, and so on. I haven't been there yet, but it's quite interesting how this last 50 years urbanization. That's just one example. If you look at other places growing fast, in China or in the west of the United States, there are similar interesting examples. So urbanization is a big thing. Now, but they think about urbanization as of course, giving shelter to people, but also impacting environment. And the impact could be on land cover and, of course, pollution of air and water, emissions, and also some local climate change, because the so-called urban heat island effect, when temperatures are higher in urban areas compared to surrounding areas, or average temperature inside the city can increase due to the high density of construction materials, because these impervious surfaces like pavements, roofs, they are not acting like vegetation. So this is this I put this to understand better what's going on when you have an urban sprawl. And first of all, when you have an urban sprawl, then you have an increase in auto dependence. Those people that live in suburban Jerusalem have to drive much longer distance. Longer distance travel has more traffic congestions, if you understand. And this leads to more air pollution. And greenhouse effect is more pronounced because we exhaust CO2. And that leads to the effect of climate, because climate is affected by greenhouse effect, everybody knows. Besides that, we also built more impervious services, like highways, buildings, parking lots, which are usually a replacement of the previously vegetated areas. So you have a decreased carbon sequestration. If you remove the grass, which absorbs carbon from the air, by pavement, which doesn't, it affects, of course, climate. Also, there is a runoff of water, so-called non-point source water pollution. So it affects also the aquatic environment, which leads to decreased water quality and ecosystem health. So from this, you would imagine that urbanization with all the services to people really not so good for environment? Well, not always. In semi-arid areas, and Israel is probably part of it, the conversion of agricultural land to suburban space results in increased ecosystem services through establishment of suburban forests. Especially in the west of the United States and Arizona, whenever they start building something, they also plant vegetation, they build swimming pools, they provide services which improves the environment. So the concept that urbanization may be a good thing is counterintuitive, but in some areas this appears to be the case. Now let's talk about a little bit about climate. 35% of anthropogenic carbon emissions since 1850 resulted directly from land use. Well, let's separate land cover and land use and climate. And I could bring examples for each of the areas for human-induced or natural effects and back between land cover, land use, and climate. Just don't have time for everything, but you can think about it yourself. Most importantly, there are two kinds of feedbacks. And when they talk about climate change, they mostly talk about biogeochemical feedback, greenhouse effects. We emit a lot of carbon, which affects the temperature. That's what usually the spiel that is given to the public. Changes in terrestrial biomass, so chemistry, microbiology, leads to changes in atmospheric chemical composition. But, of course, atmospheric chemical composition affects by itself also the growth of vegetation. With more carbon, there is better growth for vegetation until a certain level. But there is also biogeophysical feedback. Because changes in surface albedo, roughness, moisture availability due to changes in landscape affect changes in surface heat and water fluxes, radiation, momentum fluxes, and vice versa. If you change this flux, they will change also the variables that are describing the surface. I'll follow up on that, but I just want to finish with carbon. That there is a certain imbalance of carbon, in carbon stocks in forests. Because they think that if you plant forests, then you have a good impact on carbon in the atmosphere because it absorbs carbon. So afforestation or reforestation is taking place in various countries as a positive initiative. We just have to remember that it's small annual changes in carbon stocks over long periods of time. It's not immediately start working. Whereas deforestation, removing forests, it's a large changes in carbon stocks over a short period of time. Once you cut forest, carbon is released immediately into the atmosphere within a year you have much more. So imbalance occurs because most emissions from deforestation takes place rapidly, whereas carbon removal from afforestation and reforestation activities is a slow process. So because of this incompatible timescales, you have this imbalance. So people that think that planting a forest immediately improves the situation is not for sure, because also there are activities that may override very quickly this effect from what you think was happening. Now I will talk about what was modeling showing us. Clearing the boreal forest has a strong cooling effect in global circulation modeling that was found out already long ago. And growing forests, instead of clearing, growing Eurasian forest has a warming effect on simulations. Why is it so? These are results of simulations by a general circulation model showing that the net global radiative forcing in some areas where you have snow may be giving you the overriding or the opposite effect to what was expected. What I mean is that the initiatives that were developed in China, for example, to plant forests to say we're good because we absorb carbon, if you do it in the area where albedo before planting forest was already high because of snow, by planting forests, it reduces the albedo because the reflectance of forested area with snow is lower than without snow, like steppe or any area that. Now, when you're reducing albedo, it means that will be more absorbed radiation. So the net radiation may be opposite to what you would expect in this case, and the decrease in surface albedo by forestation may be as important as carbon sequestration, which is by geochemical effect, in its forcing climate, which means that forest carbon sinks in some region could exert much smaller cooling influence than expected, or even exert an overall warming influence. So those people who work on only biogeochemical process, they are forgetting about other parts, this biophysical feedback, for example, albedo. And there are other things like roughness and moisture availability, but I'm just saying that it's a complex problem. So to understand the human influence on climate and the impacts on land cover, a complex range of effects must be considered. Not just one process, but the whole system of processes that some impacts could be balancing each other, and some could be overriding even what's expected. So in the 1980s, they developed this system of interactions. Don't try to understand it so quickly because I can compare it with the Tokyo metro map that was even more complicated. So let's go further. Land use impact on biological sources and sinks of carbon. There are 7 of them affecting carbon stock changes. 3 kinds of conversion, from natural ecosystem to permanent croplands, from ecosystem to shifting cultivation, ecosystem to pasture, abandonment of croplands. That happened a lot after breakup of the Soviet Union, that people left their agriculture, and the agriculture fields started being overgrown by bushes and forests. Harvests of timber and establishment of tree plantations. What was promoted by Roger Pilke, who is a prominent scientist in Colorado, and in 2005, which is already 17 years ago, he was promoting this. That land surface modifications by humans may actually have a greater impact on climate than that due to anthropogenic greenhouse effects. So I'm trying to open your mind to not to think to just this part, which is mostly publicly promoted. There is another part that's often being forgotten. The way humans alter the surface of the Earth may be a key factor in climate change, and tropical land surface changes, that was his finding, that probably great influence on climate than the seasonal El Nino, weather disturbances in the Pacific. Conversion of forest to agriculture may lead to local temperature increase comparable to that due to addition of carbon dioxide into the atmosphere. So here showed that the changes in land use can dramatically alter weather patterns. If you change land surface, it leads to changes in precipitation and temperature. Changes in vegetation pattern soils could change cloud formation, precipitation. Change from grassland to agriculture leads to cooling effect. Changes from forest to croplands to warming effects. So there is a direct effect of land surface alterations to mesoscale convection, for example. Models of cloud convection of the central US show the storms can develop over current agricultural landscapes that would not have occurred over the original prairie land. This is an example of human and of the factors that should be taken in account in models. This is fire, natural anthropogenic fires. They affect atmospheric chemistry. And it's known that majority of fires are human-induced, and 97% in Spain, 60 to 80% in Russia. So it's an important subject. For example, a project in my program by Amber Sawyer showed how different is the number of fires in Siberia from 95 to 2000 to another 5 years, from 2001 to 2005. You can see by eye that the number of fires increased. Is it because of global climate change? If so, then it's a positive feedback, because you have more fires, you have more pollution, more changes in albedo, and then there will be more warming. So, climate models try to take into consideration all the processes going on, like land physics and hydrology that we discuss now. But Earth system model already tried to take into account ecology and land use. The model that is considering chemical processes and ecosystem process offline is shown here, but the model from Hadley Center that includes this, incorporates all these connections interactively with the climate model is already considered a system coupled model, which is already the next level. And this is an old graph, so maybe they already improved and incorporated more data. Now there is a movement, especially in Europe, to the so-called digital twin. They have a special project called Destiny, which is Destination Earth, and we at NASA also start moving towards this to incorporate whatever you can in our studies, and Land Carbon Exchange Program will contribute with data on irrigation, data on urbanization. All socioeconomic data should be included in the system model to become digital twin in real time with interactions. That would be the difference between a climate model that you simulate, you change solar constant, or you change carbon dioxide, and you see what's happening there. It's a real-time processing with assimilation of data. Just to emphasize the effect of emissions, I was in Vietnam, and you see people wearing masks, not because of COVID, because it's so badly polluted. Half of the pollutions are due to two-wheelers, so motorcycles produce a lot of emissions, and in 2012 only 6% of motorcycles were equipped with catalyst exhaust control devices. So really, it's a serious problem in many countries. We have a control experiment. 2 years ago, this increase in fossil CO2 emissions that was drawn from 1970, suddenly you see a big drop. This drop is zoomed in this January to May 2020. You can see a decrease. And now the decrease by different sectors. You can see that in power, industry, transportation, public, everywhere there is a drop. What was happening? And why in residential area there's no decrease? Remember lockdown? So people were sitting at home, and they were using their power. But aviation dropped substantially. There were no flights. Remember that? So that's a control experience. What would happen if we didn't emit all this carbon in real life? Industry stops, aviation stops, but we can't stop it. So they try to have different alternative sources of energy and so on. You know all this green wave and green politics and so on. All right, now let's move time. Okay, 15 minutes to the main part, because that was all preamble from about climate system, Earth climate. Now, what is remote sensing? Those who don't know exactly what Hishami Rahok is, it's applying recording devices not in physical intimate contact with items under surveillance. Even if you direct a gun to measure your temperature, it's called also remote sensing. It's not like taking a thermometer, putting on the arm. So remote sensing is anything without in contact. But we also know that it's seeing what can be easily seen and then convincing someone that you're right. What's important is to observe areas that are remote and hostile, like jungle, volcanoes, fires, because really without observing it from outside, it's very difficult to understand what's going on. And remote sensing tools for this are depending upon the scale. So this is a synoptic scale from 100 to 10,000 kilometer region, which you have to observe with satellites because it's too wide for airplanes to cover. Something of a 100 kilometer scale, probably airborne observations would be sufficient, but there are also flux towers that you can put within 1 kilometer, or you can have process studies within meter. Remote sensing can be roughly stratified into optical remote sensing, thermo-infrared, and microwave remote sensing. Optical remote sensing can be stratified into passive and active, as well as microwave passive and active. Passive can be stratified also by the resolution, coarse, medium, and high. And active resolution are LiDARs. That's what you measure with the sending signal, receiving it, and processing it from satellite, on the ground, LiDARs. Probably everybody knows, but in microwave, active observations are in radars. Those who have a microwave oven at home, it's actually a radar. Besides satellite and airborne observations, we use in situ observations, like this level, and modeling, integrative data analysis that I showed before. In data information systems, very important to build something that can process all this data incoming. So you see that now, NASA has already 50 years in space of various missions. Some of them are important for studying land surface. These are Landsats, Terra Aqua. There are 2 satellites here with MODIS on board, and some NPP, and there are also some sensors that are on International Space Station. And the most recent one, Landsat 9, was launched in September, and NICER is the future mission with radar. It's NASA India mission. So the most relevant from systematic missions for studying national solar during 25 years have been Landsat 8 and Landsat 9 most recent. SOMEN PP is a continuation of Terra and Aqua that will be discontinued soon with the MODIS sensor on board. We consider its coarse resolution. And Landsat, we consider moderate resolution. And there are also exploratory missions like a shuttle radar topography mission, which built during 1 year global topography to correct Landsat data for geodetic disturbances. PO1 had the predecessor of Landsat 8 on board and the first hyperspectral sensor. And also I mentioned that there are some sensors, instruments on board of International Space Station from 2018. There is EcoStress with thermal infrared channels, JEDI with LiDAR, 3 lasers, and the hyperspectral German sensor. History of Landsat is long. Landsat has been since '72, so we celebrated 50th anniversary of Landsats now. They usually had a couple of Landsats in space, except for the time when Landsat 6 was launched and went down to study deep ocean circulation. And now we have two good Landsats 8 and Landsat 9 with 30-meter resolution. Since we have systems with different spatial resolution, they could be used synergistically. Those that observe daily, and with daily coverage every 2 days, for example, those are very coarse resolution, hundreds of kilometers. And those that are moderate resolutions with 250 to 1 kilometer resolution, these are MODIS. But medium resolution, like Sentinel-2 and Landsat, they observe with 30 meters, but their repeat cycle, the same point at Earth, is seen only once in 16 days. With 2 Landsat, it's 1 in 8 days. If you have cloud, then you have once a month. And if you have both time clouds, you have nothing. So what's important is to have as much data as possible with this resolution, and that's a multi-source imaging. But there are also commercial systems that you have to pay for, that have now Planet Lab. Is a company that has 200-something satellites in space that already provide global coverage with 3-meter resolution. I'm not talking here about Eros data and Israeli satellites that also you can buy data from them. So 1 to 3 meter resolution. Okay. And that's what multi-source imaging is, to try to put a combination of, how many minutes?
2 or 3, leave some time.
All right, so the idea is to use synergistically different satellites to increase frequency of observations and optical, and then if you have microwave, you have opportunity to observe the place where you have clouds more often, like in tropical areas, even better, because radar sees through clouds. When you zoom in, you're talking about this commercial data, and those who don't know, they have to look into Planet Lab datasets because they are available. They provide universities limited datasets for free. Also, if you are working on tropics and tropical areas, Norwegian government bought Planet data all over the globe, so 3-meter resolution over tropical belt is available for free. And 3-meter resolution, you can actually count trees. Okay, next. Besides NASA data or NOAA data, there are other data. And there was a so-called Department of Defense satellite, the DMSP satellite, OLS sensor, that produced night lights. And this is a mosaic of night lights for just 1 year, 2012, that you can see a mosaic for just 1 year. But the idea is to look in time. And here's a composite of 1922, 2000, 2009. And when you know how red, green, blue is mixed, you would start seeing interesting stories. For example, why this is bluish, this area, as compared to Eastern Europe. Bluish means that the blue is giving intensity, whereas red and green don't. Why is it so? Blue was 92, and these are later. What happened in 91? Everybody? The breakup of the Soviet Union led to the collapse of economy, and these republics, former Soviet Union, Ukraine and Moldova, suffered most of it. That's probably seen better. I called it the decade of collapse, 92, 2002, and then the recovery, 22, 2010. You can see how urban center like Moscow grew, expanded in colors. In the color means that there was light intensity source for growing. And you can see also how during collapse time, Ukraine suffered the economy went down. And probably in the future, I will add another graph, another collapse. What's happening now is half of Ukraine is probably dark. And then it will start growing. So it will be very interesting to monitor how it will restoring lights and how it will become prosperous, whereas Russia is unknown. It's like a hole. I could stop now, but I wanted to mention that I worked also on aerosols and there was my interest was to show the potential of AVHRR, how much you can derive from AVHRR that could be used in meteorology. And that's the American Meteorological Society bulletin of 2000. That was just when I moved to NASA. And one of the variables that I calculated besides all of this was effective droplet radius. Which showed the effect of fires in Indonesia during El Nino. And it was based on the algorithm that was developed by Professor Rosenfeld here when we were collaborating and calculating effective droplet radius. And unfortunately, he is not here. But we showed that the smoke penetrating clouds reduces the cloud droplet size, which reduces the rain potential in clouds, which provides positive feedback of the drought that was happening, which leads to more fires, which gives more smoke. So it's an effectively is a positive feedback. There were two waves of during this El Nino. First is showing here what was happening when it was in October, when the smoke penetrated clouds. So it was a lot small droplets. And then what happened when the rains came in and cleared up the area, and then you see that the rain had much larger particles in a smoke-free atmosphere. But that was long ago. He moved, of course, to new results and so on. He probably would correct me if I'm mistaken somewhere here. So that's the rain system arrived later than usual, but in late November the rains put out the fire, so the end of 97 was relatively fire smoke-free. Now I see here a lot of young people, some of them left, so they won't know my last remark. If you torture your data long enough, it will confess. Thank you very much. Toda raba.